Hello guys, I'm Duki and welcome to my programming video. The aim of this video is to showcase the implementation of a C++ library for creating RESTful APIs. There are many libraries for this, but unfortunately most of them are so user-friendly that they encourage developers to switch to Python instead. My design allows implementing various RPCs and serialization processes with as little code as possible, keeping it intuitive to read, requiring only a minute of reading examples to learn basic usage, while avoiding problem-causing approaches like macros or code generation. I will also strive for competitive performance and embedded friendliness. I will use C++ 17 with the parts of C++ 20 that are widely available now. Some features of C++ 23 could make this even better, but it's going to take years for them to become available, so I'm going to ignore them here. The GitHub link is in the description below. The first and rather difficult step is to give it a name. All the descriptive names are already taken, and already similar to whatever I might come up with. Shortcuts are often hard to remember, and thus I have decided to simply pick a word that's unique enough. For reasons I will not reveal, I'm calling it Bomba. Because the namespace ending brace will be far away from its start, I'll better comment it. Let's start by implementing the serialization functionality. Remote procedure calls, or RPCs for short, will be built on top of it. Although I won't put much emphasis on object-oriented programming, we need to provide some basic interfaces for improved versatility of the code. The serialization functionality should be provided through a common interface, all RPCs should be accessible through a common interface, all REST API protocols and all serialization formats should be usable through a common interface. Now I've created an interface called iSerializable, with two abstract methods, serializeInternal and deserializeInternal. Because abstract functions need to be as versatile as possible, they are not very convenient to use or implement. Because of that, they aren't public, and there are three public facade functions that expect a data format as a template argument. Data format is a concept that is met when the class contains two classes. One of them implements the iStructured input interface and the other one implements the iStructured output interface. Now let's implement them. Here is the iStructured output interface. All write value methods are meant to write different non-nested types. Nested types will generally be some sort of arrays or some sort of tables with named elements. These may also be called objects or hash tables. Nested types usually have a starting syntax, an ending syntax, and some kind of separator between elements. The elements may need to be numbered, and it would be inconvenient and also inefficient for the implementation to keep track of the ordering, so the functions are provided with indexes. In Json, it's necessary to know which element is the first in order to put comma separators properly. The indexes for named elements are also provided both to mark when to put commas in JSON and possibly also to allow some sort of table indexed by both numbers and strings akin to tables in the Lua programming language. Because there might be reasons to write some elements differently, for example to dictate where to use XML child text and when to use XML arguments, bit flags may be passed as an argument. They are in a namespace instead of being declared as an enum because it's practical when it's convertible to integer. Again, this interface isn't practical, but the user of the library won't be using it directly unless extending something. To illustrate what I meant with the interface, I'm adding an implementation for JSON. I'm making a header only because it will be converted into a C++ 20 module once its GCC implementation is stable enough. Here's the implementation of the interface for JSON. C++ 17 has added a nice function called stud2chars for efficient and local independent conversion, but for some reasons its version for float is not available in GCC yet, so this nice private member function I have written for this will not be used in the case of using double. String needs some escaping, so new line quotation mark, and of course the escaping sign will be escaped. The only non-trivial part is the implementation of JSON arrays and objects, because it needs to keep track of the depth, so it uses a member variable that saves the depth, and the new line function indents it accordingly. Before I write the I-structured input interface, I need to decide about error handling. Using exceptions will be the most intuitive and straightforward way, but a lot of codebases disallow exceptions because they are deployed on restrictive embedded platforms or for other reasons, often just because of the myths that surround them. So it will be possible to configure it to do something else than throw exceptions when a parsing error happens, and because that probably won't exit the function prematurely, it will pass a boolean value marking that it failed. Here is a function for throwing exceptions that can be replaced by something else if a macro called bomba alternative error handling is defined. It throws an exception that inherits from stud runtime error and also uses its constructor. If someone cannot use exceptions, he can define this function elsewhere and have it log the error message or something. Here's the parser interface I came up with. It definitely doesn't look the most practical, but again, it will only be used to FS8. It comes with several functions for parsing non-nested values, some functionality for parsing arrays and objects. The ones for getting the next elements return if there is a next element. In the case of object, also its name. So far, it's quite similar to I-structured input. For the case where exceptions are not produced, there is a public member called good, and it's set to false if an error happens. The parser is supposed not to produce any undefined behavior if it's set to false. This is more convenient and more efficient than returning if the operation succeeded. Compared to I-structured input, there is also a method to identify the next variable type. This will have a rather niche use in a statically typed language like C++, where usually only one type of the data value is acceptable. To implement some sort of polymorphism without identifying everything, it's possible to store a position. Then, to run through the object without parsing it, seeking for a property with a certain name, this is called SIG_element, and then to restore it and start parsing it as the proper type. Here is the implementation of the interface for JSON. It has a bunch of utility functions for reading through the input while making sure it doesn't look behind the end of data. Its constructor is quite straightforward. The function that identifies the type skips through the white space and separators as defined above, then checks for the next character, and then tries to decide which type it was. Because JSON does not allow values like none, only integer and float can start with the same characters, and even these can be easily told apart by the presence of decimal dots or exponents. Parsing integers can be done using the stud from chars function. This should be also done for float, however GCC does not implement this even if it's part of C++ 17. String has to deal with escaping, so it's not just a copy. Bool and null are pretty easy because we just need to check for misspellings. Arrays are also straightforward, objects are also straightforward. However, seeking for elements in object without parsing them is more complex. It needs to keep track of the nested depth and also string quotation to avoid finding these members in nested objects and string values. If it finds a string that's actually either at the start or after a comma, it parses it and then checks if it's the one that was looked for. If it's not found, it returns false. Dealing with the position is simple because the position is simply an integer member here. It might be more complex if it was doing actually some sort of unarchiving or something. And it's actually pretty ugly, but I didn't think there was a way to avoid it because it's obvious that with this relatively ugly error handling and this not really nice interface, there's not a good way to do it. There's still one little problem with the interface. It needs to use dynamic allocation, which can be a problem on many embedded platforms. Although I have not used any new or delete, stat string will dynamically allocate if its size is greater than 15 plus terminating 0. In certain cases, some sort of fixed size buffer with helper functions for manipulation may be needed instead. This could have a common interface for moving every single character, but that would be a performance problem, and it would also require writing facades over every possible string type. This can be avoided quite well by returning a string view. There is a little problem with string view that it actually does not own the data, so it will have to be owned somewhere. We cannot just return a substring of the data that's provided, because most strings need escaping, and also there might be some hypothetical format that actually uncompresses something. My decision to deal with this ownership is that the implementation will need to hold a single buffer to deal with this, so the returned strings will be valid only until the next call. But that's not a big problem, because they will only be used for lookups and copying into target variables, so not a big deal. This allows turning the Json class into a template that can work with other string types. All they need is to satisfy a concept that expects them to have the plus equal operator overloaded for character and cstring, also to be convertible to string view, and also to have a clear method. The user can thus define a JSON for the string type that suits him best. Now, here's the basic idea of the code that allows serializing combinations of types while giving all of them the same syntax. These two functions, serializeMember and deserializeMember, will serialize and deserialize an integer. This isn't very interesting, basically just does the same thing as the interface. However, now it's possible to create a concept for types on which these functions or one of their overloads can be called, and for a vector of types that can be serialized using existing functions. The concept for vector does not require a complete vector-like functionality, only the functions that are needed. Then the vector can be used as an argument for another overload, and we can just now serialize vectors of types that already can be serialized. These make the interface of the serialization interface just more bearable, but it still has some way to go. Other types can be done similarly. Float, bool, string, objects inheriting from iserializable stud array, and smart pointers are quite straightforward. Maps, ordered or unordered, can be handled by the same code. It has a little complication that when deserializing, extra element needs to be discarded, preferably without adding dependencies. I decided to solve it by creating another map, updating all present elements and moving them there, and finally swapping the two maps. Because a container with members that can be used with serialized deserialized member can itself be used with serialized deserialized member, these rules apply recursively. Now, a large, or mathematically speaking, infinite variety of member types can be serialized and deserialized with the same generic code. Now, let's find a way to generate the listings in the virtual methods automatically. If you thought this was too simple, this is the time when it starts to get complicated. For the next step, I think the Godbolt compiler explorer will be more suitable than the previous editor. So let's say I have a class like this. And I want to serialize it without actually writing some extra methods that list the members. It is possible to do through a free function, but I'm not able to get to the names of the members, so I would only get some sort of list without actual names, and that's not quite what I want. So I want to name them somehow, and I figure out that this is the shortest way it is possible to get it working. This cannot be done without some sort of members, and I will need a parent class for that. It will also implement the interface I need. And to get this working, I found that it's necessary to turn it into a CRTP. And because this makes it impossible to actually give it the default value, because this looks like a default value already, I might be able to insert the actual default value like this. And this is actually doable. Key can be a member of the serializable parent class. It returns some special value, which has an overloaded equals operator, and the result is convertible to all kinds of classes. And that way it syntactically can be done. So let's implement it. This is an implementation of the serializable class that compiles and illustrates what is it meant to do. It gives information about the serialization and uses this information to implement the serialize internal and deserialize internal methods. The key methods return an instance of the initializer class that is a part of the initializer class that basically can create the variable be initialized from several arguments that are passed to its constructor in the makeType method. Calling its conversion operator will make the actual type, but it will also have a side effect that adds two functors that provide the serialization and deserialization. Assigning to this type will actually create the instance of this broader type that's specialized to this argument. It needs a little workaround for Microsoft Visual Studio compilers to work, because this compiler can construct some classes from stud initializer list and trigger ambiguous conversion errors. The hard part of this problem is to implement some mechanism that would determine these offsets. Determining the offsets is difficult because the parent class never gets references to the members. Still, I am aware of 4 ways of determining the offsets of members in a class. The first one is to grab the size of the parent class and use the size of the member types to calculate where the next member will be placed, taking padding into consideration. A problem with this method is that a type that isn't intended to be serialized will be skipped in this calculation and cause undefined behavior. The second method is to try to aggregate initialize the class and check what the initializer objects were converted to. This, however, comes with some relatively restrictive requirements of aggregate initializable classes, though it is still very useful for determining the class constructor type. The third method is to construct the return value as a local variable, save its address and return it, relying on copy elision that the local variable will be actually kept at the return address. This works with all compilers I have tried, but unfortunately not with primitive types. The fourth method is to fill the class with garbage in a controlled way and check what was overwritten after initializing every member. This one is the least restrictive, so we'll use that one. Here's how the algorithm works. First, all bytes of the child class are initialized to repetition of a special value. This has to be done in the parent class's constructor because the object's bytes are memset to 0 at the beginning of the constructor unless it's default initialized, which it isn't. The child's size can be determined using CRTP. We are going to exploit the rule that members are initialized in the order they are written in the class, from the ones on top that are saved on lower addresses to the ones on bottom that are written on upper addresses. The initialization of the first member sets a value which tells what was the last byte set to a certain non-garbage value. The initialization of the second member finds the first changed byte, since the initialization of the first member, thus determining where was the first member created. It also saves what was the last updated byte, so that the third value can determine its position using the same mechanism, etc. This process is repeated twice with a different special value because the default value may happen to be exactly the same value as the garbage value. These special values should better be odd because pointers to dynamically allocated objects will not break it, as they are guaranteed to be aligned toward size. So the class will have to be experimentally created twice when starting the program, and then everything will be set. So here is a feature complete version. To prevent confusion, it's better not to call the constructor 2 more times during a regular constructor call. All the serializing information is placed into a structure. This structure is a static inline variable that's basically just like a global variable. It's initialized by a function that's called before main. This has the advantage that actually nobody attempts to create it before, but also it prevents us from using some things, one of which is stud another map, because its hash seed may not be initialized at that point. However, a stud vector of pairs is faster if there are less than a few dozens of elements, so it's no problem. First, the initialization function creates the result structure that's going to be initialized, then a helper structure that keeps a pointer to it. It saves a pointer to this helper structure to another static inline variable that just important only during the setup. This is more convenient than dynamic allocation because it's faster and we can't forget to delete it. The child structure is allocated into a buffer using place menu and destroyed using explicit destructor. This is called by a special helper type that just makes sure we don't forget to do it near the end. During this process, the constructor behaves slightly differently because it finds the helper structure. If it finds this helper structure, it checks the initialization state that's always different in each initialization run, and sets the bytes of the child class differently. The conversion operator behaves also differently in this case. First, it actually checks where is the garbage and where are the members, so that it could be later inferred where these members were actually written. And also, during the first time it's run, it fills the vectors of functors that do the serialization. As you can see, it infers the positions correctly and can serialize the class with this little code. But it could be better. These vectors of functors could be avoided, allowing better inlining and avoiding unnecessary embedded unfriendly dynamic allocation. They can actually be made at compile time, but this requires the craziest trick on my list. So let's get into it. I have not discovered this one. I have found it while looking for something else in the third reply to a question Stack Overflow, which was itself the fifth result on the third page of server results in the 10th query I tried after finding only replies that it couldn't be done. This is an equivalent to finding it in a forgotten tome in a secret section of a lost underground library on an uncharted island. The whole thing was explained with a single line in a Russian blog, fortunately in English, and mentioned in a YouTube video with 2000 views after 5 years. And even that one showed it only as, hey, somebody showed me this code, I have no idea how it works. It's actually an unintended implication of the standard and works to some extent on all three major compilers. It's listed on openstud.org as defect report 2118 or stateful metaprogramming via friend injection. It's there for 6 years. It was decided that it shouldn't work like this, but no mechanism how to prevent this was not determined. So here is the trick. First, I declare a struct with a forward declared friend function tied to its type. Next, I define a template class which defines this friend function. We cannot call this function because the template is not instantiated, and therefore it's only forward declared. So if I do here some retrieve, it fails because there is an undefined reference. It's only forward declared. However, it doesn't matter where I instantiate this template, it will always become part of the code. So if I just do it here, it's actually defined, and so this forward declare function actually works. And therefore, from absolutely any context, I can export a const per value and get access to it at whatever other context I want, as long as it's in the same compilation unit. Cool, right? This can be extended to save and retrieve arrays of values. If declarer is a template class, then setter can set it for specific template arguments with different values each. Then it's possible to assign the results for each template argument, and whenever we decide to retrieve the value for a certain template argument, we get the one we assigned. Unfortunately, this triggers a warning on GCC, but it can be suppressed. Expanding arrays can also be done because sphinai can be used to check if a function was or wasn't added. There are multiple ways to do it, but the only one that I found that works on all compilers is to forward declare the function as auto, then to define it in a way that returns the actual type, and then it's possible to query for its existence by checking if the return type is what it was supposed to be. The instantiation of add to array for the first time will fail to match the template specialization because boolean declared wasn't created anywhere, so it creates setter with starting index at 0, so it will instantiate boolean declared for index 0. Next, if it's called again, it will match this condition, so this specialization will be used, which will again look for add to array with index 1. However, for index 1 no boolean declared is known, so this time it will match this version, and setter will be instantiated for index 1 using the value prepared for that. If done again, it will cause it to match the specialization twice, and finally create setter with index 2, etc. This way it's possible to add elements always at the lowest unused index at the time. I can also look at them and see that I'm getting to new and new indexes. Adding the same element twice is not possible because the template will already be instantiated for that combination of arguments, and compilers assume that metaprogramming is stateless, but that's not a problem in our case. This is an example closer to the serializable class. Two values are stored, a function pointer and an integer that can be changed at runtime because it's a static variable here. This is much like the serializing function and the saved offset. They can be saved, for example, as pointers to lambdas without captures, because these can be converted to function pointers. Once C++20 is properly supported, it will be possible to use these as template arguments, but at the moment it's not supported by all compilers. When this is done, it should be possible to iterate through all the existing instances of setter to call all the retrieve function and use its appropriate retrieve value. This has to be done with recursion and recursive stop. So these individual values can be then saved, and when we're iterating, they will be retrieved and properly used. However, there is at rep. The problem is that the compiler compiles the code as it's going down, so the state changes and the order of the definitions of functions does matter. For example, in this case, if main is before actual this add to array is called, it finds the array empty and it prints nothing. If I go it back, it prints it again. Although this isn't necessary for the task, it's possible to let the compiler know the names of the members at compile time. C++20 allows using string literals as template arguments, so I can construct a constexpr object from an array of characters. This is a case simple enough for automatic deduction guidelines to apply. For convenience, I have defined a bunch of functions that are similar to string, so it can be used in ways that are quite intuitive. In more recent C++ versions, constexpr functions can be written quite similarly to regular ones, but I have experimentally determined that the compiler is better at optimizing them when they are written recursively. I have found that the method of inspecting the child class using defect report 2118 can't be used on Clang or Microsoft Visual Studio compiler because the templates are evaluated in an unfavorable order and I could not find a way how to force it to do it in the order I wanted. This means that much more of the code can be done at compile time and properly optimized on GCC, at least before C++23 reflection comes out. In order to support the other compilers, I had to leave some of the old code to do the parts of the task if macro no defect report 2118 is defined. I have replaced the usage of stat function by pointers to instantiation of template functions, which can be inlined if known at compile time. The serializer storage and serializer saver classes are needed for injecting the state at compile time. The addMember class can be instantiated to instantiate the serializer saver class with the right properties at the right index. Object info can be used to provide the serialize and deserialize functions, which are recursive and go through all the members to serialize them. It has to be instantiated after all members are set, and it also provides a getOffset method that returns an array with the right size to save the offsets into. The setup function still has to be called. The offsets have to be determined at runtime, but it only needs to return a dummy bool value if we can use this trick. The method of saving the members is now different, and it needs to be used somehow to avoid a warning, and also we need to use the result of the setup function somewhere, otherwise it would be optimized out and the side effect, which we absolutely need to get the offsets, will not be produced. The virtual functions called the prepared object info serialize and deserialize methods. Another change is the key variable, which, well, used to be a function, now it is a variable. It's now a template, inline, static, constexpr variable. And it has the advantage that it allows calling the key without actually using the parentheses, and this has no overhead because it can be completely optimized out, because, well, it has no members and only its operators call some code. The unoptimized assembly looks much like a translation of the C++ code. If I enable full optimization, it's much more inlined and much more obfuscated. Here's the serialized internal function. It's actually very inlined, difficult to tell what this code is doing. It does make some virtual function calls. However, it also makes some calls to string operations. This is interesting because it means that the compiler was able to devirtualize the virtual functions. In this case, it was able to notice that there is only one implementation available in this section, so it's going to use that one implementation. This should be really fast because it's just one function that actually is capable of deserializing the entire class. If I optimize it for code size, there is some RTTI code. It says that there are 450 lines of code. Much of this code is just some error handling. With disabled RTTI and exceptions, it might be even shorter. So this should play really nicely with devices with only a few tens of kilobytes of program memory. Now it was time to implement the RPC. Before I start, I need to show this utility class. It's needed for the cases where a remote method is called, which requires the client class to create a request, have the protocol create a header, then write the request and have the client finish it and send the request. This can be done by calling a method in the client class to return a prepared header, add the request into it and have it send it, but doing so without dynamic allocation is tricky. An alternative is to call the client and supply the reference to a lambda that writes the request so that the resources for sending the request are allocated on stack. An interface cannot use lambdas because each is a different type, so I written a callback class that creates a facade over lambdas with the same call signature. It's basically what stat function does, but without the overhead and complexity pertaining to type erasure. It's a specialization of a template type that is unusable itself. That's a convenient way to make the template arguments look like a function type and not like a list of arguments. It's only an interface. Then there is a function that wraps around the lambda and turn it into an ad hoc class that implements the interface. This can be done using a helper function with template arguments deduced from the signature of its function call operator. The helper function is in a nested namespace to avoid polluting the main one. It creates a wrapper class that basically just redirects everything into the lambda, and it all can be pretty much optimized out. The return value is the lambda with an added interface. The Rpc interface needed a few auxiliary classes. One for identifying sessions, relevant only for protocols supporting some kind of authentication. The next one is the request token for identifying responses to requests, which is useful in case there is some kind of client asynchronicity. To have the interface send requests, it needs an interface for network clients. This is done by the Rpc responder class, which has a method for sending the requests with a callback for actually writing them with all the resources allocated. Then a getResponse method for reading the responses to specific requests with a callback for parsing them, and an auxiliary method for checking if the responses are available, which may be useful in case there is some kind of asynchronicity. The main interface for the RPC is iRemote callable. It's meant to allow the methods to form a tree structure where child classes are callable through the call method or can contain nested classes which can be accessed through the getChild method. In case it's a server, in case it's a child, it can learn its path using the child name method. Then there are some protected methods to allow the child to get access to its instance of the Rpc responder, which is useful only for the client. I have written default implementations for these virtual functions to avoid code application. Again, this is an interface. It will have utility classes for more convenient implementation. Most protocols nesting classes through a remote callable would compose the procedure name from names of parent objects separated by a certain short string, most likely a single character like dot or slash. To implement this together, I have created a utility class for parsing or writing paths while going through the tree. All of its methods are static, but it's more convenient as a class because of the template arguments. The find callable method finds a method with a given path. It has quadratic complexity, but it shouldn't matter because it's unlikely the separator would be long enough and the inner loop can be unrolled since it can be optimized out because the separator string is known at compile time. I'm using a goto for breaking from double loop. That's actually less error prone than an extra control variable, and so it's basically one of the things goto is still good for. The construct path method is recursive. It searches up the tree to locate the parent, then it writes the path as it returns down the tree. Because only the first iteration needs to create the string and only the other iteration need to add a separator, I had to make two versions of it, unfortunately. Here is a proof of concept of giving an Rpc interface to a class. I needed a way to cause the call to be redirected to the server if the object is a client, and to convert an Rpc message into a call if it is a server, somehow knowing the argument names and possibly some additional information, all without splitting the information into multiple locations or duplicating it. I figured out that the most readable way to add names to arguments would be to inject these as default values to arguments. Unfortunately, function pointers do not work with default function arguments at all. However, there is a way to work with a function with default argument. If it is a lambda, then its type can be used to carry both the function and its default arguments. So I'm wrapping it in a class that provides the extra functionality and derives its behavior from it. The type must be fully specified in the member type definition, so the lambda must be part of the type. This wasn't doable before C++20, however, now it is. Doing it in line comes with an unpleasant restriction. The lambda cannot capture this pointer as it isn't the class's scope. It would be doable if the lambda was a default value, but member variable type cannot be deduced from its default value since that one can be replaced in a constructor. The pointer to a parent can, however, be supplied as the first argument. This makes it somewhat worse than I'd like it to be, but I have not figured out a better way. At this point, it only works as a server. The Rpc Lambda class does most of the magic. It can work with the types of arguments and also with the return type. If the first argument is a pointer to a class that's derived from a remote callable, then it's considered to be the pointer to the parent object. During the setup, it creates a statically allocated data structure to save the setup information into. Then it calls the lambda with all the expected arguments omitted to let the name function do its work. The name function has to be a free function because the lambda is not part of the parent class's context. It returns a type that can be converted into anything, allowing to initialize any argument type. It has a side effect to assign the variable name into the data structure, which unfortunately has to be a global variable. For thread safety, it's thread local. To avoid actually running the function, the last argument's construction does not return, using one of the evilest mechanics in C++. You have seen me use goto before, but this one is much worse. This is the first time I have ever used it actually. The std long jump function discards the stack made after set jump and continues from there, this time with a different return type. This is super dangerous because no stack unwinding takes place, distractors of stack allocated objects are skipped, and optimization may go wrong because functions are expected to return. Because of this part does not use any objects with custom distractors and writes into volatile objects only. The resulting structure with the collected information is used to initialize a static inline variable. Calling the function relies on converting a stud tuple into function arguments using stud index sequence. At first, the tuple is created. If the first argument is a pointer to the parent object, then the parent is converted into it. If the block with arguments is present, then individual arguments are looked up and assigned into appropriate tuple members using the recursive setArg function. This function goes deeper if the argument name is not matched and ends once it gets out of range. The call itself needs to handle the void value, especially because a function cannot save its result into a variable of type void. This means that some code needs to be duplicated. As you can see, these two lambda wrappers correctly respond to requests. The getMessage call returns the value of the message member that was set here, and the sum call returns a sum of its arguments. However, there is a problem. The order is incorrect. It's 3 and 2, but here it's 2 and 3. Also, here you can see that names are first and second, but they're actually listed as second and first. This is because the order of initialization of variables that are used to set the default parameters of function calls is unspecified. And this is a problem that cannot be ignored. Here's the fix for the unspecified order of default argument value creation. The call with a part of args function recursively builds a tuple that will then be used to call the function, first with one argument missing, then with two arguments missing, then with three, and so on. In every iteration, there is one argument that wasn't seen yet, and that one will be added at the lowest index. This isn't particularly efficient, but it's run only once at the start. Now I've added the client part. The main problem was that the Rpc Lambda class itself had no variadic arguments to be used for its call operator. They could, however, be made available in a parent class that was templated to the call operator of the Lambda. Because I needed access to the first argument to identify if it's the parent object or not, I had to make two versions of the parent class. One for lambdas with no arguments and one for lambdas with at least one. To avoid application, they have a common parent class. The one with no arguments has void for the first argument, which is impossible for a real lambda. Both have to be specializations of a class, as is necessary to turn a template argument into a group of template arguments. Their common parent is the old class. I have added the function call operator. I needed three variants of it, each restricted to a different lambda type using the requires clause. The first is for lambdas requiring the parent object, the second is for lambdas not requiring the parent object, and the last one is for lambdas that do not expect any arguments. All of them try to obtain the responder. If they get it, they send the request and read the response. In case they don't get it, they just call the lambda. The request making function recursively goes through the arguments and serializes them. The response reading function either deserializes the response or reads an empty response and returns void. Fortunately, the return value of a void function can be returned, so there is no need to specialize for it. When it was done, I changed the code to static inline variables or defect report 2118 in order to easily extend it later to additional kinds of members, not only member structs. Each member will keep a function that will get a child method with a certain name and a function to obtain the name of a child member method at a certain address. The way they are saved is similar to what was used in Serializable, either a simple struct or a bunch of forward declared functions in a template class. In the case of defect report 2118, they are retrieved using two functions in structs using partial specialization to recursively search through all child objects. If defect report 2118 is not used, an inline static vector of information is constructed using an instance specifically constructed for this purpose. It's not as necessary here as it was in serializable, but it is convenient and thread safe. Looking for names of child objects or their instances is done either by iteration through the prepared vector or by recursive functions looking at the functions holding the information. Initialization is done either by children detecting the parent class being initialized and adding the information into the vector, or by instantiating a struct that would trigger instantiation of the friend function, creating the struct with the right index. For now, the functions dictating how the child objects should be looked up are simply context per static lambdas. The next step was to write a communication layer. I decided that the easiest way to get the protocols right would be to make an HTTP server first and try to use a browser to communicate with it. Plain HTML does not provide a good way to show a reply, so the only thing it can do is to display a new page. Trying to serialize the response into an HTML template would lead to some sort of PHP clone, so I decided not to deal with showing a response for now. Here is a piece of code that provides an RPC method and a web server to allow displaying a formulary in the browser. The caching file server class loads all files in the directory and puts their contents in a std_another map, allowing to look it up quickly. I know that std_another map is not the fastest hash table around, but it's conveniently available. The Rpc getResponder class decides if an HTTP GET request was an RPC call or if it was just meant to download a file. It can be replaced by a custom class to use the result of the RPC call to modify the page, but I consider that a bad practice. The HTML post responder class is a class that directs HTTP post requests to an RPC method. Then an HTTP server is created based on the pointers to these two objects, which meets the concept requirements imposed by the TCP server class. TCP server only cares about keeping sessions, reading TCP streams, asking the protocol where requests end, and sending the responses back. Its run member function keeps it waiting for requests and processing them until stop running is called. The main difficulty with TCP server was that std experimental networking is badly documented and implemented only partially. Well, because it's experimental. Its GCC implementation looked like if it was written to run only a few test programs. The client one seemed to be better. However, it had the huge advantage of providing a dependency-free operating system agnostic way to implement networking. The HTTP protocol is relatively boring code like any other protocol. An HTTP parse state class parses the header entries, ignoring most, and is interruptible for the case the packet ends in the middle of a header. It's followed by a few functions for escaping and unescaping strings, which is made more complicated by the problems that URL might not support UTF-8. Then there's the HTML message encoding class that implements the iStructured input and iStructured output interfaces for using HTTP requests by RPC classes. HTTP requests are somewhat limited and don't support any kind of structure within structure, so it's not as useful as JSON. These are some helper classes and concept mostly for customization of GET and POST requests. The HTTP server class links this all together, although it deals only with parsing the first line of response, writing headers, and error handling. A somewhat more interesting problem is that the header has to contain the size of the response content, but the size of the response is not known before writing it, so that it doesn't have to be copied. This is solved by writing a placeholder space as content length and overwriting it with the actual size once it's written. The object is initialized first by creating the IO context class, either by the number of threads or not, which makes it single-threaded. Then a pointer to the class implementing the protocol is saved, and then it binds to the socket at the selected port. Also, it opens the port. In the usual cycle, Connections are being accepted, creating new sessions. A session has a socket, a session of the protocol, a buffer for reading data from the socket, a stud vector buffer for assembly messages, a pointer to the parent class, and the index in the vector of connections to allow its safe removal. It waits asynchronously for something readable to appear in the socket or calls the callback with 0 size of incoming data, which is a signal the connection was closed. For some reasons, GCC expects the functor to be callable with both 1 argument and 2 arguments, so it needs a default argument. When the data is read, it's copied into the leftovers buffer with the messages, and then read leftovers is called on it. The function uses the protocol session to read the data and provide a response, or to ask for more data, or to exit the connection. Client ID doesn't like it because stud span is implemented with concepts and it doesn't support them yet. For some reasons, the socket has to be closed before being destroyed. A similarly boring class is the caching file server. Its constructor and call to its reload method scan the supplied folder structure and fill a hash table with the file's contents. The scan goes recursively through folders and saves all files that were found into RAM. It uses a stud-shade mutex which allows simultaneous locking by many threads that access the cache, but locks exclusively when reloading. After creating the server, I have also created a client. I aimed for convenience of usage so the client is synchronous, although it has separate calls for sending a request and waiting and processing a response. It implements the Rpc responder interface, so it can be used to allow Rpc classes to send requests. This piece of code uses the same method as the server, but adds a client to it and calls it for each line it reads from stud_scene. The sync network client class is not very different from a typical Boost SEFS 8. It creates an IO context, a socket to connect from, a resolver, and an endpoint for connecting to the server. It keeps the responses as vectors of cars indexed by their identifiers. Sending requests is somewhat trivial, just writes into the buffer. Getting a response first checks if it was already received while looking for another response, and if it wasn't, it reads the responses from the buffer. If it's just checking if the response was already received, it stops when the buffer is empty, otherwise it blocks and waits until it's received. The HTTP client class uses a lot of stuff already written for the HTTP server class. It implements the Rpc responder interface, so it can be used by the Rpc objects for communicating with servers. The implementations of its virtual functions mostly redirect to public methods. The send method sends a post request, overwriting the placeholder spacing with size after serializing the request. The get method sends a get request, which is straightforward. The get response method asks the networking client to provide it with replies, preferably with a certain index, and parses them. If it's the right response, it calls the reader. If not, it returns the identifier so that the response could be found quickly when actually requested. If a part of the response is missing, it also notifies the server about that. It also returns the offset in the range so that the client knows where the message ended. Meanwhile, I refactored the callback class because it was complicated, inefficient, and overly verbose. It is no longer a Voldemort class returned by a function that is taken as reference to its parent. Now, it takes a pointer to the constructor argument and creates a free function that takes this pointer as its first argument. It doesn't own the object at all. The other arguments are passed as const references because I found them the most convenient in this project. Perfect forwarding requires arbitrary references that don't fit all use cases or universal references that may lead towards error messages. The JSON Rpc server class is a stack of the HTTP server class, a custom class to handle GET requests, and the JSON Rpc server protocol to handle POST requests. JSON Rpc server protocol's POST method handles requests that can be both alone or in a JSON array, while each of them may or may not produce a response. The code for responding to requests is rather long and complicated because the JSON structure has no internal representation and is parsed mostly linearly. There can be no output if the request has no ID. However, the order of arguments in the request is unpredictable, plus there is some explicit error handling. The reason why I did it this way is that it's very efficient. It seems to add only about 1 microsecond to the response time. The JSON Rpc client class inherits from the JSON Rpc client protocol class and injects an instance of HTTP client into it. Because members are initialized after parent classes, the HTTP client is a member of a dummy parent class initialized before, since it's on the left. The JSON Rpc client protocol class implements the Rpc responder interface and has 2 methods, one for sending requests and one for receiving responses. Parsing is much simpler here because it doesn't have to deal with all the variability a proper JSON Rpc server has to handle. Next, I wanted the system to be able to provide its own description. JSON Rpc does not specify any format for API description, but a similar protocol, JSON WSP, does, and that format can be used to describe JSON Rpc as well. It both describes composite types used in the API and the actual remote procedures. It would be inappropriate to fixate the library to a single protocol, so I designed several interfaces that should be universal enough to be implementable for any protocol. The iProperty description filler is for adding members into a composite type. The iSerializable description filler is for adding additional types appearing as members of this type, and then to obtain the iProperty description filler for this type. The iSerializable interface was extended by iDescribable serializable, which can also provide information about its members. For describing methods, there is the iMethod description filler for filling parameters of methods and iRemote callable description filler for adding methods and composite types used by the methods. The types should be added first because most protocols would define the composite types first. iRemote callable was also extended for listing composite types and methods. The implementation of the JSON WSP description is quite repetitive because function arguments are described differently than the return type, and composite types members are different from both. I use inheritance to deal with the most repeated parts though. Also, the iStructured output interface turned out to be quite inconvenient for this. Some refactoring is needed to deal with this unexpected technical debt. I have also made a few edits to the Rpc object class to implement the extended iRemote callable interface. Now a single function can generate the API's description. To expose this description, I have also edited the caching file server class to allow adding variables as downloadable files. Now the JSON WSP description can be downloaded. To make this usable in scripts, I have written a JavaScript file that uses this description to generate and evaluate code to create normal functions and GUI blocks that run these JSON Rpc methods. It's not exactly the most idiomatic JavaScript, but I was lazy to go too far from what I'm used to in C++. I have also added some CSS to make it look somewhat acceptable for this decade. Like JavaScript, it's not a language I know well, so certainly there's some room for improvement. But in my defense, very little of it was copy-pasted from the internet. So I use this code to self-document and use it to create an UI from. It can store some data, it can retrieve the data, it can make some operations without accessing the state, and it can write to the standard output. So this is the result. As you can see, it's a working UI for the code. In order to deal with the technical debt pertaining to serializing dynamic structures, I have added 2 helper classes to the iStructured output class. ArrayFiller opens and closes an array in its constructor and destructor, introduces members and counts the objects. ObjectFiller is similar, but unlike in ArrayFiller, writing members also expects names. Both ArrayFillers and ObjectFillers can start writing nested arrays and objects. However, to deal with the circular dependencies, the method of ArrayFiller that returned objects had to be defined after the class and declared as returning auto. This shortened a lot of code, eliminated a major source of errors, and helped me fix a bug that my unit test didn't catch. I have tested the performance and found it to be quite good. When testing the web server performance with JMeter, the reply speed was about 60,000 requests per second single-threaded with turbo disabled. That is about twice as much as what Nginx could reach. I suspected that the main limiting factor was in the TCP layer I was using, so I tried the same using large writes on local hosts. This ended up in transmission of huge packets with lots of requests in each of them. The server was able to process as much as 600,000 requests per second this way, or 1 million if turbo was enabled. As for parsing packets, it seems that parsing an HTTP message takes half microsecond more than parsing a binary message. Parsing a JSON RPC message takes about 1 microsecond more than parsing an HTTP message. However, the time to process a TCP packet seemed to be as much as 5 microseconds, so the limiting factor was clearly elsewhere. And that's it. There are a few alternate implementations of things that could be added, like some binary message format, SSL, UDP, peer-to-peer, etc. But telling about that in this video would be repetitive. Here is some code using it, implementing both the client and the server in the communication. If there is no command line argument, it becomes a server. If there is a command line argument, it sends it to the server with a hard-coded address. If there is a flag called notify, it sets the second argument to true and it will sound the terminal's bell.